In this video, we're going to be talking about the rate of change of the angular size. Okay, this problem says a boat sails directly towards a 150-meter skyscraper, that's here, that stands on the edge of a harbor. The angular size of the building is the angle formed by the lines from the top and the bottom of the building to the observer. The observer's out here. Okay, so we've got this right triangle here, and we've got the height right here is 150, and we have this distance between the boat and the bottom of this building being x. Okay, so what we want to do is find the rate of change of the angular size d theta dx, so that's a derivative, when the boat is x equals 500 meters from the building. Okay, so we need to relate theta to these two things. Okay, and we're going to do that with trig. There's two different trig functions that would work. There's tangent and cotangent. I am going to use cotangent. Cotangent theta. In trig, we learned that that's equal to, in a right triangle, that's equal to the adjacent side, which is this bottom part right here, okay, divided by the opposite side, which is this one right here. Okay, that's how I'm going to do the problem. Now, quickly, you can use tangent too. I'll show you how to get the derivative of the tangent before we do the cotangent. So you'll need to pause the video for a second here if you want to see this. Okay, we are going to do it with cotangent, and we're going to find out that the derivative is going to be the same either way. Okay, so we'll set up this cotangent equals adjacent over opposite. So that's cotangent theta is equal to x, that's the adjacent, divided by 150, which is the opposite. Okay, so the next step I'm going to do, I want to solve this thing for theta. So I want to get theta by itself, and the only way I can get rid of this cotangent that's in front of this theta is to apply an inverse theta to that. So I can say that I have cosine or cotangent inverse of cotangent of theta. Okay, now we have to also do that to the other side, so it would be cotangent inverse of x over 150. Okay, now the cotangent inverse and the cotangent will cancel each other out, so we will get that theta is equal to cotangent inverse of x over 150. Okay, so now we need to figure out what the derivative of this thing is. Okay, so recall that the derivative, I'll write that in a different color, the derivative of an inverse cotangent function, right here, cotangent inverse of u of x. The reason I'm putting u of x is because it's not just an x inside this cotangent. There's a function in there, x over 150. So I'll write u of x. Okay, so the derivative of cotangent inverse when there is a function on the inside is this, negative in front of the fraction, and this will be the derivative of the inside, the derivative of u of x, divided by 1 plus the u of x term squared. Okay, so let's go back over here to the function and take the derivative. So we get d theta over dx is equal to, okay, so the derivative of the inside. So what's the derivative of x over 150? Well, the 150 is the same as just a number out in front of x. So it would be 1 over 150 would be the top. Okay, here's the fraction. Don't forget my negative that's out front there. Okay, and then on bottom, we have 1 plus and the function squared. So x over 150 squared. Okay, we need to clean this up a little bit. Okay, I will leave the top alone for now. I'm going to clean up the bottom. Okay, so let's go ahead and square that out. So it'd be 1 plus x squared over 150 squared. Okay, and then I'm going to combine these two down here. with a common denominator, the 1 and this fraction here. The common denominator would be 150 squared. So I'm going to change this into a 150 over 150, and then I'll add those two together. So the top would be 1 over 150, my negative sign, and then I would have 150 divided by 150 plus x squared over 150 squared. And excuse me, I meant to say these two have to be squared because the denominators have to be the same. Okay, when the denominators are the same, you can add those up into one fraction. So the top is still 1 over 150. Here's my negative sign out front. And I get 150 squared plus x squared divided by 150 squared. Okay, now I have a fraction divided by a fraction. So I can clean that up. Let's go back down here. Clean that up and flip the bottom and multiply. So here's the top fraction, and now I'm going to flip the bottom one and multiply. So the 150 squared would go on top, and the 150 squared plus x squared would go on bottom. Okay, we're almost there. One of these, this is going to cross reduce, so this goes away entirely, and the square just turns into a 1. So we get negative 150 divided by 150 squared plus x squared. Okay, so that is our derivative function. Now what it asks us to do is find the derivative when the boat is x equals 150 meters. So I'm going to plug in a 150 to this. This was d theta over dx. Okay, so d theta over dx at x equals 500 is going to be equal to negative 150 over 150 squared plus 500 squared. Okay, and if you put that into the calculator, you'll get approximately 0.0 or negative 0.00055 radians per meter. Okay, so that's the answer. This is the rate of change of that angle. Okay, so as the boat is moving, the rate of change of the angle is changing at this rate. Okay, that's A. Now for B. Okay, B says graph dy dx, so graph this derivative function. Okay, and determine the point where the angular size changes the most rapidly. Okay, so if we're graphing the derivative function, if it's changing the most quickly, it's the farthest away from the center axis. Okay, so the center axis going this way. Okay, the farther away it is, either on top or at bottom, but farther away it is, the more rapidly it's changing. So let's go to our calculator here. Okay, so I am going to type in the function. Here it is. This is the derivative function. Okay, I got it typed in there. Okay, and my window, I had to play around with the window until I could find a good window, but here's what I used. The x min is 0, x max is 1000, the y min is negative 0.1, and my scale is 0.001. Okay, and my y max is 0. Okay, so if you're using this calculator, make your window look like this before you graph it, and then when you graph it, it's going to look like this. Okay, so recall that I said that if you want the most rapid angular change or change of the derivative, that's the farthest away it is from this center axis. Here's the center axis. So we can see that it's close here, and it's farther here, and it's farthest away right there on that axis. So at x equals 0. So at x equals 0 is when the angular size changes most rapidly. Okay, so it would be at x equals 0, and you can graph that thing by hand. I did that. I'll show you where I did it in a different place really quick here. There's the graph. Okay, so that was by hand. Okay, now we can go ahead and do d theta over dx at x equals 0. Okay, so I'll plug in a 0 for x. So it'd be negative 150 over 150 squared plus 0 squared. Okay, and that's going to be approximately equal to, let's put a little couple squiggly lines here, approximately equal to negative 0.0067 radians per meter. Okay, so this is the most change at any point. Okay, so you notice that when you're at x equals 500, it's way less change than that. Both of them are pretty slow, but this is the fastest change. And that's it.